I would love to start the Q&A session. Let me see. I'm going to allow participants to unmute themselves. And looks like Alex already has a question. So let me go to Alex. Sir?
Okay, hello. I just had a quick question for your presenter. So in Kaluza-Klein theory, I think that the idea is that gravity is curled up in the compact dimension, but in the particle accelerators, we haven't seen that compact dimension, at least at the energies we've been at. So I just wanted to know his thoughts about that.
Yes, Oscar Klein hoped that these loops in the fifth dimension are like a standing wave and could calculate the electron, but that was not possible. And Wesson uses the fifth dimension not as a loop, but as a depth in which the 4D brain dives into. And we have such a depth also in superconductivity, where magnet fields from the outer space go into the superconductor with a length lambda. And it's the same with the Higgs field. It's also such a lambda. So I look for the term. Just a moment. Yeah, penetration depth. Yes. So in Wesson sees the fifth dimension as the penetration depth, like in superconductivity for magnetic fields or the Higgs field in particle theory. And the loop were not successful. Nothing which could be derived from it. But Klein started with it, the string theory. And Kaluza-Klein theory is a quantum particle theory, not a classical as theory of Wesson. So far?
Wonderful.
Great. Thank you.
Thank you, Alex. Okay, let me see. Who else has questions for Detlef? Oh, so David Mathis. David, you had one about can the charge to mass ratio be developed from the 5D solution?
Yes, there is the expression. Yeah, the theory has a certain expression for the charge mass ratio, which corresponds to the fifth dimension and velocity in fifth dimension. But as a classical theory, it makes no predictions for a special charge mass relation.
Okay. Let me see. And who else has questions? Anybody? Please raise your hand. Michael Boyd had questions. Sir?
Hello. That was an excellent presentation. I appreciate how you were able to simplify it into such an understandable manner, and the way you were able to follow, set a timeline. And so I really appreciate that. My questions are, I'm curious if the effects would, how you could explain the frame drag effect that you observe when you have a moving mass like the Earth. It causes seems like it's like the gravitational field is behind the electromagnetic field time-wise. It slows down as you get closer to the Earth, time slows. And so how does that, how would that show up in that 5D model that you used? That's what I'm curious about.
Yes. It's been a long development till this presentation. I'm thinking about this topic for over 20 years, and saw that the mess is very difficult, and had to develop views and expressions to make it simple. And also the physical extract is important. It doesn't help to solve formulas, but you have also to know what it means physically. Yes, as I showed, the 5D metric tensor is such that the Einstein tensor of the 5D metric is 0. And splitting this into 4D and 5D components, we get the 4D Einstein theory. But the element of the lower right corner in the 5th row and 5th column appears in the place of the gravity constant. So it's variable in this theory. And you could see the gravity constant as a scaling factor to energy. The energy is the same of the electric field, but when you scale the gravity constant, you make the metric bigger or smaller. And that may be the same as moving from far down into a gravity field where time dilation slows down the development, and also the light velocity is seen from outer. Yeah.
Yeah, that's cool. So would that mean then that depending on whether the objects or the direction, I guess it's moving, and the velocity, the speed of the gravitational propagation may not be the same as the speed of light. Correct? Would that be correct?
No, I don't think. I think the scalar field will move with light velocity as light does and gravity does, because it's the velocity of space-time, or the velocity of 5D space-time. And here light, the 5th dimension, and charge is the velocity in the 5th dimension. And the 5th dimension itself is the mass over the penetration depth. So it's a very complex theory. As the cover of the book shows, it's like a clockwork. Everything graphs into another, and as I saw in the solution, with the Lorentz transformation of the electron or the charge solution, the charge gets a magnetic field and is contracted in distance, and also the scalar field behaves the same. So if we have two charges circling and emitting electric dipole field, this could change the gravity constant. And also the changes in the gravity constant could radiate from the center. Or perhaps it's only a hollow. So when the charges circle and radiate electromagnetic field, it may be that the gravity constant builds a hollow, and the 4D metric sinks deeper and deeper and deeper, making
So
the gravity
would
constant
that
stronger
mean-
or lower. Pardon?
Would that mean that the electromagnetic field and the gravitational field could be independent from each other, or are independent from each other? You could have a gravitational field without an electromagnetic field, and vice versa, correct?
Yes, yes.
Okay. So in your equation, though, you have like the fifth term for the gravitational energy is. So that's like that fifth term can be. So what I'm thinking is the fifth term can be independent from the 4D tensor, correct?
Yes, perhaps let me show this slide again.
There you go.
Just a moment. Where is it? Just a moment. Yes, here it is. In the third row, we have the 5D tensors and sorted the components with a 5 in the index to the other side. So here on the left side is the Einstein tensor in 4D, and on the right side is an electromagnetic stress energy tensor in 4D, and additionally a stress energy tensor from the scalar field. And instead of the gravity constant, here is phi square. So there's also a scalar field with a scalar energy. And if we take this solution from Liu and Wesson, it's seen that the electromagnetic energy density is 2 times stronger than the scalar energy density for the solution of a single charge. And this shows that it's not independent. It's always an electromagnetic field is accompanied by scalar field, except phi is constant, because then the derivatives of phi vanish. We have to have varying phi. So here everything is connected with everything. It's very complicated. But
Yeah, but if there's no charge, if there's no electric charge, it's
Yes.
electrically charge neutral, then you can throw out all those terms, correct?
Yes. Here the G mu nu are not dependent on the fifth dimension. If you make the G mu nu also dependent of the fifth dimension, then you get another stress energy tensor, which can be shown being mass density and pressure. So also the stress energy tensor for matter is possible to deduce, but for it we have to have a dependence on the fifth dimension. So if more and more terms are zero, we get into the Newtonian limit, where only the 1,1 component is non-zero, or is deviating from 1, and it's the Newtonian limit for weak fields and slow velocities. Then the diagonal elements are 1, like in Minkowski space, only the 1,1 component in the time has the Newtonian potential for gravity as the metric component.
So would it be safe to suggest that gravity or gravitation is like a fifth dimension?
Yeah, it's a 5-dimensional gravity. Yes, it's,
So I'm saying the 3 dimensions,
Gravity.
space and time are the 4D, and then the 5th dimension would be the gravitational dimension. That's what I'm asking.
pardon? Could
I'm
you say it
asking
again?
you, in your opinion, I'm asking your opinion now.
Yeah.
In your opinion, would you consider gravitation to be a 5th dimension, with the space and time being the other 4 dimensions? Or would you say
Yeah,
it's
gravity
more complex?
is a curvature of space and time. It's yeah, space, time, and matter. And with the 5th dimension, also charge becomes additional
So there's
jointed.
gravity and charge.
Yeah.
Would be the 5th dimension, is what you're saying.
Yes, gravity has only one source, mass,
Gotcha.
and electromagnetism has 2 sources, plus and minus, 2 charges, and gravity has negative energy, and the self-energy of charges is positive. This is a great difference.
Agreed.
Okay. Well, Michael,
Thank you for your answers.
Thanks, Michael. Okay, so let me go now to, let me see, HT Alvarez, and I'll have to read this. As I recall, HT doesn't have a camera or a mic set up. He said, thank you for your excellent, useful, and well-detailed explanation. And then he's asking, in his 1826 masterpiece, Ampere reports on an anomalous Newton's third law exception between orthogonal currents. Why isn't it found relevance in space-time physics, gravitomagnetism, and propulsion? Detlef, is that something you could speak to at all? And this is a chat question. I'm not sure if you can see the chat.
Yes, I see it. I have to understand it. Why it has not found relevance in space-time physics,
Yeah.
gravitomagnetism, and propulsion. Yes, I know Faraday made experiments in the shot tower of the parliament, but found no effect on falling charges, no difference. And I don't know what Ampere found. He used a lot of complicated wire constructions and to rule out different effects and to get the right laws. And I don't know what the exceptional effect was. I think we have some hints about this. One is the Biefeld-Brown experiment, where two charges are circling and shall move faster and faster, also in vacuum, and also rotating superconducting magnets shall cause an effect. But that is much more complicated because in the coordinate system at rest, there is no electric field, only a magnetic field. But when you use the coordinate system of the rotating disk, as we saw, the space is curved, and because of the distance contraction, the charge density of the material and of the surrounding matter is different. So in the rotating coordinate systems, there are a lot of electric fields, and it's difficult to calculate what happens. And
yeah. Now also, let me see, Lulu had a question. Lulu, let me ask you to unmute so you can ask that yourself. She was asking about pions. She has, there we go.
I was asking if the pions would act as a charge that could go through the gravitational and the electric field, or even higher. It's, you know, I'm not an expert. I just read a lot, and in what you described, you know, that kind of came to mind as a question.
Thank you.
The Kaluza theory is pure classical.
Sorry, I had to mute. I'm sorry, Lulu. There was an echo. I'm sorry, Detlef. Go ahead, sir.
The Kaluza theory is pure classical theory and doesn't deal with particles. So
I was asking about the particle's charge.
Yes, I think it's
The pion's charge.
Yes, and what shall the pion's charge do?
They spin. They have a rotational spin, so they don't abide by gravitational or electromagnetic field. So that's why it came kind of to mind.
The theory only has the gravitational force and the electrical force, and nothing more.
Right.
And
She said they are independent of each other.
Yes.
On the fourth dimension and the fifth dimension.
The fifth dimension seems to be related to charge, as charge is velocity in the fifth dimension, and the fifth dimension itself is related to mass. And so you get the charge mass relation by the velocity and the fifth coordinate. but it doesn't say anything about particles. And,
Ion is not is just an energy. It's an expression of an energy, a form that can, exist like beyond any kind of force that we know in physics. That's why, I bring that, because a pion is not just a, part of a particle, but it's also an energy. It's a charge that can exist on, independently from anything else. It could just, go through things. Like, a pion can go through planet Earth, for example. Nothing can affect it. So would that be a field, like, which you were describing, like fifth dimension, fourth dimension? Would it? I mean, that's a dimension on its own, because it could go through anything. It doesn't, abide by anything. Just it's a collisions, and that's how it kind of degrades into, which is called something called a pion.
Yes,
It exists.
I don't know anything about the particle size theory, except that a scalaron is thought about, which would be responsible for the scalar field. And for the electric field, we have the photon. And I think the pions act in higher dimensions than the fifth dimension. But I don't know. I'm sorry.
So it's a higher dimension. Higher than fifth.
Yes, higher than the fifth dimension.
Okay, so that's, thank you for answering my question.
Okay.
Okay, thank you, Lulu. And again, my apologies for muting you repeatedly. We were getting echo from your speakers, but let me apologize for that. Let me see, does anyone else have any questions that they wanted to ask Detlef? We're ahead of schedule, and that is fine. We actually have lots of stuff to present today, so. Oh, Michael, do you want to go again? Go for it, sir.
So this, I'm just curious, this pion question. How do you know there's such a thing as a pion if you can't measure it? Is my observation. So it's kind of a theoretical construct, isn't it? You just don't know.
I don't know. No. I wanted to present. Oh, okay. I don't know what is the field of pion.
Yeah. Okay.
It's,
So what's your feelings on string theory with 11 dimensions?
yes, for gravity and electromagnetism, 5 dimensions are sufficient, but we have also the weak force and the strong force, and the strong force with 3 charges and field particles with mass. And it's you need a lot of dimensions only for the forces between quarks and gluons. It's beyond the Kaluza theory.
Gotcha.
Thank you, Michael. Okay, let me see. And I should ask if anyone else has questions. And again, we are way ahead of schedule. Detlef, I appreciate your staying with us and answering all these questions. Let me see, does anyone else have anything?
I have one statement. perhaps.
go for it. Go for it. Absolutely.
Yes, I'm looking for a picture. Just a moment. Yes.
And I think since we're so far ahead of schedule, actually, I think Frank Milburn will probably come on and join us, and unless you had more to present, but I
Yes,
think
I can show it later.
oh no, it's completely up to you. It'll be a few minutes.
Okay.
I would say go ahead, sir. Go ahead.
Okay. Do you see the picture? Normally we have 3-axis X, Y, Z, which we can display in perspective or screen. With 4 dimensions, we have a problem because we can only show 2 dimensions and time. And with 5 dimensions, it's even more problematic. So I drawed the 4 dimensions of space-times like a cross into 4 directions. And perpendicular is the 5th dimension, which has to be slanted. So there is a projection for the 4 potential on 4D space. But when we have no charge, the 5th coordinate is perpendicular to the 4-axis of space-time. And if you connect the ends of the arrows, you get a pyramid. So for me, a pyramid is a symbol for 5D theory. Yes, you have the axis, the space-time, 4 space-time dimensions, and the 5th dimension. In this presentation picture, they form a pyramid, and the pyramid could be a symbol for 5D theory. It's just my opinion.
Wonderful. Thank you. Thank you so much. Thank you so much. Well, so again, we are way ahead of schedule, and there's no problem at all with that. But I think what I'd like to do is put it back on gallery view, and everyone, please give a giant hand once again for Detlef Hoyer. Dr. Hoyer, thank you so much for presenting. Okay, and yeah, and it's challenging material, and I think that was some of the difficulty with the Q&A part of it. So